So today we will, okay, let me share my screen before. Um, okay. So last time uh, we have defined the T statistic, and we have defined the T test and the Z test. So the T test is a test for the mean of for a numerical variable. So we also did before that the binomial test. So the binomial test was a test for categorical variables with only two choices. For categorical that have two possibilities. One with probability P, and 0 with probability 1 minus P. So up to now, we have always considered only one column of the data we observe. So this time and for the next of the course, we will consider more than one variable. We will consider bivariate variables. Why? Well, simply because, like, if we look at a person, we want to make a guess about his height. If we know, or his weight, we want to guess his weight. If we have information on his height, our guess will be much more accurate. So basically, we want to consider bivariate data because they contain more information than simply the two columns alone. So, for instance, let me do an example. So, so the bivariate data can be, for instance, let me use the same sample as I mentioned before. So the heights can be like let me give some numbers. So let's consider the Moscow population as usual. So the number of citizens of Moscow, let's assume, is like 1 million. It is more, I guess. So the heights, let me give some random numbers. And the weights may be related to the heights. Okay, the heights, let's center them around 170 centimeters and with a standard deviation of 2, let's say. These are simply random numbers to give an example. Of course, they are not realistic. And the weights can be related to the heights following this relation, for instance. The weights are the heights divided by, say, 3, plus some noise. Some random numbers with mean 0 and standard deviation, let's say 3. And we can collect the data into a table. So we have our good bivariate data. So let's plot them simply to visualize them. So the x-axis, I plot the weights as it is usual to do that. And on the y-axis, the heights. So we can run this chunk of code and look at the points. I guess I don't know why it's taking so much time. Um, so, okay, this is not a good sign. John point, I don't know actually what the difficult part was. Okay, maybe I should restart the the program, but okay, let me continue. So now why it is so if we like compute the mean, if we look only at the two columns separately, we have much less information. And so even if we want to look only at the heights, it may be useful to consider also the other columns. And this is a reason, for instance, okay, maybe, okay, this is, I have plotted too many points, so, but this is like, let's say I'm visualizing the whole weights and heights of the Moscow population, for instance. As usual, this vector, it is not accessible to us, so we can only take samples. For instance, we can perform this code here. We can take sample size, and we can take only, let's say that the sample size is of 100 people, can take that data and take a sample of 100 elements and then plot it. Okay, let me save this sample into sample. Sorry. So, and let's see what, okay, should become everything. Okay, now we can, the image we look at usually has the following structure. So this is a sample from the real population. So also in this case, what I wanted to remark is that we look at samples from a real population. But this time, we collect for each person two data, two or more data. And as usual, we don't restrict ourselves to real populations. So by population, we mean either a real population, or we can also refer to, we can also also a random variable is an abstract population. Also a random variable can be seen as a population from which we sample. So, for instance, we can generate a function that generates bivariate data. So, a function like generate bivariate data. It's a function that we are going to define. It takes in input how many. Okay, no, let's say it simply returns. It takes no input and it returns like I don't know, a vector where x x1 is like a normal of mean like 160, say, standard deviation 2, and and x2 is a normal, an exponential, let's say, of variable 1 and one exponential of rate 1 plus x1, let's say. So these variables are dependent. X2 is defined in terms of x1. So let me see if this is a correct way to put a function. So yes, it is. And let me try to run it. So okay. It is okay, maybe it should return x. This is the right syntaxis because okay, let me see if x now it's a bivariate data. Yes. Okay. Let me put some more weight to the exponential. So I can generate this bivariate data with this machinery, with this code here, and I can replicate this many times. So I can take like replicate k times like, and sample. And let me see now. Okay, it gives me a list of so a list whose element these variables here that I generated with this function. So probably I can simplify it to be an array, but let me define like the sample x is simply the first row, and sample y, well, is simply the second row, and the data collected, the sample, is simply the collection. So the data frame generated by placing these two samples. So we should, and we can plot it. So let me see first if it is correct, and then plotted. So John point. You see, we have exactly the same image. So from the point of view of statistics, we don't care whether the sample is taken from a random variable or from a real population. So also in the bivariate case. So what I wanted to say is that also in the bivariate case, it is indifferent. It, it plays it plays no role. So it is the same whether we are sampling from a random variable, from a bivariate random variable, or from a real population, as long as we can take samples. So is it clear, this fact? Robert, am I recording? Let me see it, because I forgot if I... Mm, yes, I'm recording, sorry. Okay, so this is the usual framework, and now we can compute all the statistics. So see, look, I mean, think. So this picture, if we sample first from X and then from Y, we cannot draw this picture because um, so it is a complete different picture than doing this chunk of code. Let's say we had the previous data, which was the one of heights and weights. So we can also sample from can take like data from this data and sample pairs from the heights. How many? What is the sample size? Well, we have defined the ensample, and we can and save it into sample dates. And then do the same with the weights. But if we go and look at the picture that we can plot like sampled heights and sampled weights, and we see that there is much less information. Why? Okay, let me use the same ggplot. Okay, I had to put the converse. Okay, no, it's the same in this way. So sampled heights. Okay, let me do. Okay, now it is this picture has much less information. Why? Because basically we took the x-axis and y-axis like independently, and this is the point I want to make these days, this lecture. That is that bivariate data has much more information than sampling from separately from the two variables, heights and weights. So, and I want to give a concrete way of measuring, like measure a statistic that depend on both variables. So, which is the covariance or also the correlation, which can give you a measure of how much like data behaves jointly, not only separately. So I can start with the more quantitative part now, and recalling what is independence. So let me recall what so to the definition of two independent variables. So let let x and y be random variables, such as the height and the weight of a person. Uh, so the variables are independent, so not really as the height and the weight of a person, which are dependent, but like, I don't know, the weather, the weather in Madagascar and the income of, I don't know, Elon Musk. Let's okay, let's define what are what is independent. Are independent if for each interval let's say intervals AB and AC, sorry, CB. This probability factorizes, so the probability that X is in this interval AB and Y is in the other interval is equal to the product. So this is the definition of independence, and the meaning is that if X and Y are independent, we cannot infer anything from the values, let's say, of X on the values of Y. So let's try to plot some independent variables, which well, we did it many times. So R allows to generate almost independent variables. So let's use this fact, and let's first define two intervals. So so the first interval it is like sorry. So X will be a normal of like 100 elements, and Y will be an exponential of 100 elements. So they are independent. We know that because we are generating them. And let's set two intervals. The first interval it is minus. So first, let me plot it. So the idea is that the distribution of the vertical of the points on the vertical axis does not depend on where on the x-axis we might restrict. So if we fix two intervals, let's say -1 and 2 and 0 and 1, we should see more or less the same distribution on the vertical line. So let me simply highlight them. Uh, let me do first the first rectangle, which is from -1 to 0. And and y goes from -infinity to infinity. And we fill it with blue, let's say, and alpha for 0.01. So 0.1, sorry. Let's see if this is a correct code. Uh, y max. X min y max. Okay, so now this should, okay, the points that fall into, if we look only at the vertical points, at the at the points on the vertical, their heights in this area, which is of different color, it is the same as if we now know, like do the same chunk of code. Let's do
I
the same.
see.
Hmm? Sorry, was okay, no, it was a random noise or was a question? Okay, probably a random noise. Okay, so we do the same for another interval. Okay, another one, not the same. So that goes from 1 to 2. And we should see like, okay, now it's a little bit different because we have fewer, okay, it doesn't depend on how many points we have here. So here, of course, we have much more points because we are closer to the mean of x. But if we have, but their distribution on the y-axis is the same. So there is, let's do it, let's do it again. So we will obtain, okay, maybe it is a little bit more. So let me take more points. So we should see less difference. So you see, the vertical points really distribute in the same way because they are independent in each interval. This is the meaning of independence. And we can do it for every interval, and we can see that it is the same. Now, let's plot also for completeness two dependent variables. So I copy and paste this code here. But maybe let's take real data. So let me go a little bit. There is this, maybe I can pass it to you if anybody of you is using this coding alongside with me. So I can give you the link to like, how was it called? Okay. No, this was okay. HB2 dataset students. Uh, No, it was HBS probably. Uh, okay, probably. Okay, maybe I have, if I did a. No, that is it. Students' scores. Okay, this was a data set about students' open interest. Okay, this one was like was a data set. Okay, maybe I can pass this page in the chat. So, okay, I was I passed you the link of another page which will be more useful later, so you can ignore it for now. So this is the real link, and it's like CSV. Okay, there are some exams, some course grades. Okay, probably it's not the exact data set that I wanted to consider, but it will be fine because it will be correlated data. I need only that. So let me read this CSV column separated file or comma separated file, I don't know. And save it into data. Then, okay, it is saved. Then I can look at the column names, the column names uh, of this data. So we take the variables like the first two exams, and we'll see that it will be more or less correlated positively. So because if one, so let me plot it. So we do the same, but instead of passing here an x, we pass like exam. So the data is already the table data, and we simply need to pass here the correct name. So exam one and exam two, say, and let's try to see what do we get. Okay, now we need to center the intervals like in other places. So let's say between 70 and 72 and 80 and 82. So let's do it. So the left endpoint of the interval will be 70, and the right endpoint will be 72 of the first interval in blue. And in red, the left point will be 80, and the right endpoint will be 82. So let's try to see, of course, to see that. Okay, now the points, the distribution is different, even if not so much, but you can see there is some concentration here around 80, and in, on the right, on the red column, and on the white, blue column, you can see that also is around 70, which makes sense because it's like that more or less that many receive the same grade, like because this is centered on 70, but okay, there are also people who on the first exam went very well and on the second quite bad in a bad way. So these are correlated, sorry, these are not independent. So this is what graphically dependence or independence mean. Uh, this is like a refresh for what I'm going to say now, because what I want to say now is recall. I mean, we defined the covariance for a random variable. We can define so for a for a bivariate for two random variables. We have defined the covariance. So I want I will not recall what the covariance of two random variables is. Rather, I will introduce its sample analog. So I will define the covariance of a sample, and this is like the sample mean for the mean. So the covariance of the sample stands stands to the covariance of two random variables as the sample mean stands to the real mean. So one is the sample analog of the quantity. So by the way, the covariance of two random variables is simply the expected value of x minus the mean times y minus the mean. So don't worry if you don't remember what this covariance, sorry, what this expected value means, but now we introduce it for the, so for, so we introduce it for the sample. So let's call, okay, let's fix a notation. I don't know. For instance, I don't know, because x will be like the first coordinate and y the second coordinate. So let's fix a notation for the vector like z underline z. This is like the vector we sample, so it's like uh, x1, y1, x2, y2, or maybe it's better to keep the usual notation and simply, okay, so let me fix, so underline X is like the collection of the X of the first variable, and the other, so the sample for the first variable, and the Y underlined will be the second variable, and N the sample size. But in this notation, we associate to the ith observation the pair. So the ith observation is the pair x1, sorry, xi, yi. So the order, the relative order is important. Between y and x is important because so if we mix them, we lose information on the pair. And the covariance between these two observations is simply, well, we take the sample mean, so the node, okay, the node as usual, the mean of x as the mean, so the usual sample mean, and in the same way the mean of y will be same thing with y instead of x. So sorry, because let's do right type here. So the mean of y will be this one. Well, I simply change the names, so I shouldn't have rewritten them. And the covariance is simply we take the mean, but of what thing? Well, of these quantities here. So we take x1 and we subtract the mean. And we multiply it by the same thing but computed with the vector y. And then we take the mean of this quantity, so we do all these sums. So okay, it's a little bit along, maybe I can zoom out, because it cannot be seen the whole formula from here. Okay, now why this? What does it mean? This formula here? Well, let's plot. Let's go to the plot again. Let's use the same data as before. So we plot the score for the first exam against the score of the second exam, and let's plot two lines, like the first that corresponds to the mean of the second exam, y-axis, and the second one, vertical line, where at corresponding to the mean score for the first exam. Well, why I'm doing here? Because here I'm subtracting against these means, so I can visualize this. So how did I call this data? Exam 1, exam 2, y. Um, okay, call names data. Exam 1, exam 2, why doesn't, okay, why, and to use a zero length variable name. Okay, I don't get it. Here I was, okay, yes, of course. I didn't put the statics, the mapping here. So X and Y, font, okay. Okay, perfect. And okay, so x-intercept mean x1. Mm, okay, probably it doesn't inherit. Okay, and the horizontal line was simply line, a vertical line, x-intercept data x1. Why there is no vertical line? So let me try to. Not enough. Uh, if I sum a vector, it should give me like, well, not a number, I don't get it. Probably those have not, well, no, I'm really lost about this. Well, let's use exam 3. So exam 3, hoping it will be correct. Okay, perfect. Well, now let's look at the value of xi minus the mean. So let's choose a point and compute this quantity. Well, on the right of this vertical line, this quantity will be positive. So it will be positive for points on the right of the vertical line. Do you agree with this? Like the mean is this on this vertical line. So if the point is on the right, its x coordinate against the mean will be positive, and on the left will be negative. So do you agree with this? If not, I can repeat. I can do the same for the y also. So if it is clear, I can do also the so y instead yi minus the mean of y will be positive on above the vertical or the horizontal line, because above yi it will be greater than the mean by definition. So like which rectangles will be, which points will give a positive contribution. Now is the question, which points will give a positive contribution to the covariance. Well, the product will be positive if both the factors will be positive or both the factor will be negative. So when are both of the factor negatives in the first and the third in the first quadrant, while they are both negative in the third quadrant here. So let me just do some cosmetic. So let me annotate so it will be positive on minus infinity x max equal to the mean of x sum 3 and y from minus infinity to y max equal to the mean of the second x. So here, but let's take an alpha with and let's fill it with some better color. So I don't know, green. So this is the third quadrant. It will be positive. Also in the first one, it will be a positive contribution. So maybe let me copy and paste it and color also the other one, which goes from for which the x max mean will be the maximum will be infinity and the minimum will be the mean. So and the So this will be, I guess, with color. So the points falling into the colored part will give a positive contribution to the correlation, while the ones falling into the negative part will give a negative contribution. Now, there are a little bit more points into the colored parts, so I would say that the correlation is like positive. The points in the colored part will give a positive contribution to the covariance, while the other ones are negative. Of course, the deeper into the quadrants, the higher the contribution is. So you don't simply need to count the points, but I guess that these points here count much more than the points near the edges. So here, not only you have more points on the green parts, but they are also more like deep into the area. So like it will have also more weight. So I would say that the covariance, it is positive. So let me try to compute it. So the covariance, there is a simple command. So the covariance from data exam2 and data exam3. It would be like, no, why data exam3 is not found? Because I have just used them. Because okay, the covariance is 87. Now, is it big? Is it small? Depends on the units of measure. But it is positive because I don't know. Here could be like infinitesimal differences. Could be like, or can be like the usual grade for exams, which is a little bit of the order of magnitude we know. So it could be I mean, if it is big or it is small, this number has some units of measures. So I don't know the units of measure now that they used. So I don't know if this number is big or not, but it is positive. And as I suspect, these are grades done at a scale which we are familiar with. So like I don't know, there is a test. One usually grades the votes in a way that the differences are these are like sensible differences. So the units of measures, the scales which we are used to. So in this case, this would be like, I mean, it is a number which is comparable with the 80 here. So it is a sensible number. Uh, so note that the covariance has some units of measure. So it cannot be used to make general statements. So because if we say that this well, if the covariance is bigger than a certain number, then the variables are really correlated. Then I change the units of measure and they become uncorrelated. And so we need a quantity to make general statements. We need a dimensionless. So and now is the topic of correlation. So this is the correct. So this is why we introduce the correlation. So is it clear why what this quantity measures? It's like how much. So if the data is like a cloud, it measures uh, how much data you have in these two quadrants, of course, weighted by how far they are. It's like the mean of a variable of some points, like you do the weight of the, okay, you want to find a point where on the right, and okay, no, it's like a little bit, it is, of course, yes, it is like the variance, because but the variance is like for only one random variable. Well, the variance of a vector x, I don't remember now if I saved some, I have some x saved. Okay, yes, there is an x saved. I can compute the variance of x, which will be, or the covariance of x and x, and they will be, they coincide. So let note that covariance of x and x is equal to the variance. Okay, and this is what I wanted to tell you about the covariance. And now I want to introduce the correlation. So, well, mm, there are many measures of correlation. Or it is, in general, a number that between -1 and 1 without unit of measures of measure that measures uh, how so maybe let me draw some simple graphs. So the covariance will uh, so the covariance measures, like if we have some data done in this way, we want to say that they are kind of correlated. So if x is big, then y tends to be bigger. So we want to say that this is like, we want to say that, to say that it is they are positive, x and y are positive correlated. Then if instead the points are like in this way, they are negatively correlated. So like if you observe a big X, then you guess a smaller Y. So negatively correlated. So the covariance white is not a good number. Well, because if we observe this data here, this is the x-axis, this is the y-axis. Then if we change the units of measure, so for instance, we expand this x-axis, the new data will distribute like much more in a flat way, a flatter way. So now we cannot know the data uh, look looks uncorrelated. So sorry, with covariance, with a small covariance. But these are the same data. So, but here the covariance is small. Is small. And here the covariance, sorry, is the converse, of course. Uh, mm, yes, is the converse. So probably it's better to rescale the y-axis. So I rescale the y-axis, and now the data looks like very flat. Here the covariance is small, is smaller, and here it is bigger. Indeed, the property that it holds is that the covariance is bilinear. So the covariance of x times, I don't know, 10 y's. So for instance, instead of measuring in centimeters, I'm measuring in decimeters. So this is equal to 10 times the covariance of x times y. Sorry, these are, if these are centimeters, these are millimeters. So these are millimeters. So depending on the units of measure, so if we measure the haze in millimeters, the covariance will be much greater. If we measure in centimeters, it will be much smaller. So this is the idea. So simply, what do we do? Well, uh, we define the Pearson's correlation, which has this formula here. So it is denoted usually by a row of x and y, and it is equal to the covariance between x and y. We divide by the standard deviation of x times the standard deviation of y. So now this row is a number between 0, minus 1, and 1. This is the first property. The second property is that well, it has no units of measure. It doesn't have units of measure. So we can make general statements. And of course, it is implemented in R. So let's see how much really these two, x2 and x1 are correlated. So we can take core data x2 and data x3 and see. So the method is equal to Pearson, which is the default one, so I don't need to write it. And this 0.43, which is they are positively correlated, and the number is 0.43, which is big. So there is also a game, maybe I can send you the link, which is not really, I mean, it is not, I don't know, some very interesting, but it is called guess the correlation, so probably I can simply put the link. Don't expect anything which is not very funny, but you can, I was playing it before the lecture, so, but I'm really bad at it, but you can guess the Pearson's correlation. So for this data, I would say it's positive, it's 0. Let's say it looks like the one of the exam. I would say 0.43. Okay, it was exactly 0.43, but you can go to the next one. This looks quite independent, so it's really small. I would say 0.0, also 0.05. Okay, the true error was 0. The guessed mine was 0.5. This looks a little bit positive, but okay. You can play this game and earn these coins here, but at least you can see, you can guess. I mean, if you can, after a while, you become good at guessing the Pearson's correlation. So this is a stupid game, sorry. And okay, so this was my funny part, but okay, let me go to the not really the other side of the story, which is when it doesn't work, this Pearson's correlation well. It works well to see like what do you want this number to tell you? You want that if this number is positive, then if you see a big X, you expect a bigger Y. But this works well when the data is distributed as a cloud of points. It works well if to see sorry, if the data is distributed as a cloud of points. In other cases, It may be zero, it may be zero, but the data can be really dependent from each other. So let me go to the wiki page correlation. So this one. And there is this picture here. You see, okay, if the data is like a cloud of points, the correlation tells you how much it's a good measure. So it tells you many stuff. But of course, the correlation is just a number. You can define many others similar to it. And you can see that if it is not so okay, if it is not a cloud of points, the correlation doesn't tell you really much. You see, this it is zero for all of these points. These variables are uncorrelated probably, but they are highly dependent. So, thing that I forgot you to say when I was speaking about covariance. So, or maybe let me write it here. So, there is another property that rho is equal to 1 if and only if x and y uh, fall in a line. So if we go back here, so it is equal to 1 if they form a line, these sample variables. It is minus 1 if the line has negative slope. So if and only if fall in a line into a line of positive slope, minus 1 if negative. And the last property is that independent for independent variables, the real Pearson coefficient, the one not defined, the one defined using the distribution, the random variable, and not the sampled one, is zero. Therefore, we might expect that Varro is close to zero if the data is independent. The converse is not true if the data distributes not as a cloud of points, for instance. So if we go back here, this Pearson's correlation is zero, but the data is highly dependent. You see, it's only that a number cannot catch the dependency. Only one number, I mean, wants it's only cannot do for a sample. It cannot make for all the data. If the data is like this, it's good. If it is like more complicated, you should find more variables, more coefficients. So in the next hour, what I will do is introduce these other two uh, correlation coefficients. They are really quite easy, which are more stable with respect to outliers. So let me also, I will tell you later why and what do I mean, and then do some tests. So this is a random quantity. I would like to see when it is different from zero. So it is always different from zero because it's really difficult to guess to find. I mean, it is a random quantity. Random quantities, if you guess them, you will never be right exactly. But there is its real analog that can be zero. For instance, if the variables are independent. What do we need here to say is that this random quantity, we want to check if this Pearson's correlation is different from zero or not, but the real one. In the sampled one, so we have to have a test, a statistical test that tells us whether this sampled Pearson's correlation is different from zero significantly in a statistical significant way, which means that it is different from zero in a way that it is unlikely that the real Pearson correlation is zero, but I sampled, but by randomness, it gave me a big quantity. The sampled one is big. So in the next hour, I will introduce these two coefficients and a test for testing whether the correlation coefficient is significantly different from zero. And then some programming to plot the correlations. So let's do a 10 minutes break and then go on with this correlation stuff. I'm here if you have any question to ask. So okay, so share my screen and continue with discussing this Pearson's correlation coefficient. So I want to stress like that this Pearson's correlation coefficient has the same problematic that the mean has. So it depends on the outliers in a significant way. So as the sample mean does, the Pearson's correlation coefficient highly depends on outliers. So, for instance, a simple example, let's take two very correlated data. So let me plot them. They're almost on a line. So I would say that if I do the Pearson's correlation, it will be almost 1. But as soon as we see an outlier, like 10 and minus 10, not even that big, it will be like very negatively correlated. Yes. So simply one data, since it depends how much, not only on the sign, but also on how much the data is far A very far away point, even if it is only one, can change really the result. So this is one reason not to consider the Pearsons, to consider the other coefficients. So let me introduce the other ones, and moreover, another advantage of the other coefficients is that the Pearsons, this is one problematic one. The other problematic two is that it catches the Pearson's correlation coefficient catches only the fully catches only the linear relations. Instead, if we see some data like done in this way, let's say x is 1 to 10 and y is like the square of x, these are completely correlated. I mean, intuitively, they are completely dependent. So let me plot them. So plot x and y. It will be simply the square function. I would like to say, okay, that this is R automatically rescales the axis, but this goes from 1 to 10 and this goes from 1 to 100. So it is really actually it is this looks like a line, but it is not. The Pearson's correlation it is not one. It is positive. It will be close to one, but 97, not one. Instead, they are really dependent. So the other ones do not have these two inconvenience. So let me introduce the Spearman sigma. So it is really simple, the concept. So, well, um, so we would like um, so from a vector like from this vector 3 to 5, 10. So or from a general vector x equal and in okay, we have this vector, we can define the vector of the ranks of x. How it is defined, this vector? Well, we go in the first position, we have a 3. So 3, uh, so let's first order this vector. So let's take x and order them. So let's define tilde x, which is like 2, 3. Okay, let me add also an element, -4. So this tilde x will be -4, 2, 3, 5, and 10. Now we go here. We take what is the first element of this vector rank x? Well, we take the first element of x. We go and look at the position it has on the ordered vector, which is 3, is the third position. So, okay, in this case, 3 is equal to 3, but this 3 is like the position of the 3 in the ordered vector. So, bad choice from my side, but we go to the second position and we look at the 2. Okay, 2 is on the second position in the ordered vector, so another bad choice. but this 2 is like the second position in the order vector. So now it will be different, this vector, because we go here and we take the 5. Well, the 5 is on the fourth position. So this rank, we put a 4 here. Now we go here and we look at the 10. Now it's where it really, you see, 10 is a big number, but now it will be what position it occupies. It occupies the fifth position. So we put here a 5. And the minus 4, which is also a big negative number, it occupies the first position. So we put a 1. So the rank, basically, given the rank x is the vector of the like whose ith element is the position the ith element of x occupies in the ordered vector, in the vector ordered vector. So the rank is a vector of positions. It doesn't have units of measure, of measurement. And simply the Spearman sigma between two vectors is simply the Pearson sigma. So the Pearson's law, it's called, so the one we introduced before. Okay, but we don't compute it for the vectors, but for the rank vectors. So the rank of x, which is the vector of the positions, and the rank of y. So, for instance, let's do an example. Um, let's go back to this example here. So actually, I think the rank it's also implemented in R, so we can take rank X, rank Y without any problem and see these vectors. So you see, 1 is in the first position, 3 in the order vector is in the second because there is another 3. So, 2 point, okay. Here, if there are two elements with the same value, they occupy 2.5 instead of occupying 1, 2, and the other one, 3. Okay, that's a definition. Then the element 4 is in the fourth position. Okay, so and so on. You can see that, for instance, here, the first position, we can go, the smallest element, we can go and look for the first, for the 1. It is 1 in the first case, and in the second case, it is the element it is the last element, it is minus 10. And then we can compute the correlation between the ranks. And see that it coincides with the correlation between x and y, but computed using the Spearman method. And you see, it is positive because it is not really dependent on the outliers. Uh, we can also plot the rank. You see, it is more or less as the previous one, but now instead of having this big outlier, the outlier it gives rise to this element here, which is not that big so as to make this correlation negative. So it is less sensible to outliers. And it can fully catch this also this quadratic behavior. Why? Let's do it for the because simply because of this reason. Because if we go here and we compute if x was 1 to 10 and y was uh, x squared, if we compute the ranks, then we will see that they are the same vector. Uh, we can compute everything. So the rank of x is exactly the same vector of y. So the relation between x and y it will be 1. Do you have any questions concerning this Spearman correlation? It's a definition. You need, if you really need to use it, you will look at it again, but you need to, to know it exists. So it plays the same role as the median, because the median with respect to the mean doesn't really take care of outliers. So 1 point for the median is 1 point, and it doesn't the median doesn't care about if the point is really far away or not. But the mean, yes. The Pearson's correlation cares about how far are the points. Spearman's and Kendall, no. So let me introduce the Kendall tau. Probably I will simply say 2 words about it. So let me share, let me do it on the board, open board, so the whiteboard. So the Kendall's correlation is simply have some data. Well, we take the pairs, the possible pairs we can do. Mm, yes, we take simply the possible pairs we can do, and well, yes, there can be. We use 2 colors. If the pairs are oriented going northeast or southwest, then we put a red and a blue if it is the converse. So something like this. I hope I'm not doing too much a mess because I'm forgetting for sure some points, and I have drawn too many of them because I mean, there are much more edges than points. So I'm making quite a mess. So, and if they are directed either south, east, or north ovest, I paint them in blue. Then the candle's tau is simply the number of red edges, red segments, edges, minus the blue edges, the number of blue edges, and to make this number independent, I mean, to normalize this number, so we divide by the total number of edges. So that this is a number between -1 and 1. So I'm forgetting for sure a lot of edges, so sorry for that. But R does it automatically, so you don't need to draw them. So yes, I'm forgetting a lot of them. So basically, if there are n points, the number of edges that I have to write is n squared, more or less. Similar to so I have written like more than 10 points. I should draw. Okay, not really n to the power 2. It's like n times n minus 1 divided by 2 probably. But it's still a huge number, and I, of course, haven't drawn a lot of edges. But this is the way you compute, and the computer does it for you because it is a computer and computes stuff. So we can basically see that also in this case, the candle tau is 1. Yes. So these are the correlation coefficient you can define. Now, do you have any questions on these other two correlations? If not, I go on. They are important, but I mean, conceptually, they are only just a way of measuring uh, the covariance, the correlation between the two variables. Now, what I wanted to say is, okay, let's introduce, like, as I said, the test. So, as I said, like, all the three coefficients and that I have introduced are random quantities. Since they depend on the sample. And the idea is that they approximate deterministic quantities. Which are defined on through the population, so the whole population. As usual, we don't know the whole population. We don't know the machinery that generates this data. So we can only observe samples, and we would like a way to say that to test the following hypothesis. The null hypothesis is that, let's say, Varro is equal, so the Pearson's rho is equal to 0. And the second one is that it is different from 0. Okay, of course, as usual, you observe Varro, cioè you observe your sample. This is the real row, so this is like not the sampled one. The one defined on the whole population, or through the random variable. Also, the second one is the real row. We can observe var row of the sampled one. We can observe this number. If so, if we observe a sufficiently this Pearson's correlation a sufficiently big Varro, we want to reject, we can say that we accept H1 instead of H0. So how big this observed row must be depends on the test. So we can do this test. For instance, we have a nice command that is called simply core test. And we can put these two, I don't know, this x and x squared. And see the result. So in this case, it uses actually a t-statistic, and it gives me back a p-value which is very, very small. So the alternative hypothesis is that the true correlation is not equal to 0. And indeed, okay, these are not even generated, are generated by my mind. So it's not, I mean, I don't know if this is a true hypothesis or not, but I for sure I selected them in such a way that they look very correlated. But the hypothesis actually rejects H0 in favor of H1 because the p-value is very, very small. So let's try to do it for some real data. And then maybe I can explain how this test works, why. this test work, or maybe we can also do more stuff. But let me select the data that actually written in the chat, which was about okay, which is this one. So I can go to and download this file. And read this file and save the data into data student and like kind of show the column names and maybe some rows. So we had data student. Okay, is probably okay. Let me try to see if it's still alive my computer. Uh, um, mm, okay, these are the names of the columns. They are there are some IDs of students. There is the gender, the race, the I don't know what is this, the type of school in which they're going. I guess it is private, public, or something similar, and the program like scientific. I don't know. And there are some scores in reading and writing, math, science, and social studies. So what I want to do, well, is to study the correlation between these values. So this is like the data set. Okay, this is like the social class in which they pertain, like low, middle, and high. So we can study many stuff about on this data set. Let's simply look since we have introduced like we are only studying numerical variables. Let me simply eliminate the non-numerical columns, which still are important, but let's simplify. I mean, we are studying correlation. Correlation requires numerical variables. So let's take the data of the students and let me select some columns. The So I subtract to this data frame, well, the columns which are not numeric. So I didn't. Okay, it doesn't fucking pass stuff. I don't know why. Well, gender, race, whatever it means. Uh, then the social like class in which they are and the school type and the program. School type and the program. So now I can look at this dataset like, okay, it's only numerical, and I can use from the package. I don't remember really. I think core plot. I can do a core plot, so I can core plot this data, so I can add a row, compute. I compute the correlation matrix, then I pass it into this core plot. Okay, and this gives me the correlation. So blue is positive. It's a positive correlated stuff. So let me, for instance, plot before that to see that I mean, the data is well behaved. So I can plot, I don't know, the reading score versus the math score. So read and since mathematician, let's plot the math score. It's okay. So it's like a cloud of points. They are obviously correlated. Can compute, and we see the correlation plot about this. Now, do you notice anything strange in this, like these correlations? Like, yes, the reading is really correlated with the other variables of scores, but there is like a column which is really is positively correlated with the others, but really it's not. It shouldn't. Like, it's not clear why. ID is the identifier of the student. So why the identifier would be correlated with the other uh, variables. So like why the higher the positively correlated, by the way. So why the higher your ID, the most the bigger the scores, you expect to see a greater score. Why? I mean, the reason is that one takes the identifiers with a criterion. So, uh, so there is something particular going on. Why the ID is correlated with the other quantities. The fact this usually happens because the data, the ID is collected, is assigned with a criterion. And that criterion, I don't know, for instance, you send me your homeworks, I put the identifier in as like the first student who send me the homework is like receives the identifier one. The second is the identifier two. So probably the first who send the homeworks are the have prepared it in advance and not at the last moment. Maybe they are more prepared. I don't know. But this criterion with which I assign the identifiers, uh, it correlates these variables. For instance, I don't know, the identifier could be like uh, first they started with the private schools because they are more efficient and private schools tend to give higher marks because I don't know, because they want to, I don't know, it depends on also on the private school. So I don't know, there is a criterion with which you assign the identifier, which correlates these variables. So sometimes it happens. And let's see if the, I don't know, if this correlation is significant. So so let's take, for instance, the first variable, like the identifier. Does the identifier data student ID correlate with the reading score? Let's see. The test give me a p-value which is 0.03. So if we take a significant level of 0.05, the answer is yes. It is significantly different from zero, and the identifier is chosen in a way which make this data at least correlated. So um, okay, so this is the first thing that I wanted to tell you. The second one is this plot, which is nice in its own. And finally, um, okay, okay. So is it clear that to check whether the correlation is significantly different from zero, you need a test, because you will never be exactly zero because it's a random quantity. I hope that this is clear. Then another thing that I wanted to make clear is that I almost made a mistake, because like if I look at the correlation and then I do the test in a way that I pick like the highest correlated columns, this is not a way to proceed. You need to first have, actually, you shouldn't look at the data before deciding which variable to test. Because if I look at the data, then I decide which variables are the most correlated, and then I perform the test. It is like cheating, because we will see it when we introduce the Ponferroni correction. So, but I just wanted to tell you in advance this, because it's a typical error. So, the way to proceed is first to select the variables to test. Then to decide, then to test them. So otherwise, so if we test, if we decide to test a lot of them, more than one, so more than one pair, we should adjust our p-value. But the reason is that, so if we perform many times the test, we have more chance to make an error due to randomness. Like if we look at many data, we will see some spurious correlation. There was like site which like looked like correlated, I don't know, the movies of Nicolas Cage with, I don't know, the earthquakes in Japan, I don't know. You can find some spurious correlation, which are of course due to randomness, but because you are looking at many data. But if you decide to test uh, to do many tests, you should do it, decide it in advance and adjust the p-value. So this is not something that I want to tell you now because it requires a little bit to mathematical computations, which are really, really easy, but we are not doing tests. We are not doing this now. Uh, so to keep in mind, there are two stuff that first decide test and then look at the data and not decide the testing based on the data. Otherwise, you are like biasing you are modifying your p-values. And I will go back to this when we introduce like ANOVA. Then you should, if you test many stuff, you should correct, adjust your p-value. So, actually, there is a test that you can make from the package psych, so library psychology, which is called core with 2 R's test. And we can pass like the correlation matrix of the data that we have defined here. So let me copy and paste this chunk of code and see that let's see what output does it give to us. So it gives to us the correlation matrix with okay, why they are negative here should be okay. So it gives us like the correlation matrix. So now these covariances are negative. So these correlations are negative. Here they were positive. Why this is happening? Okay, but it gives us also the p-values and tests whether the variables are correlated or not. So here, for instance, in the position 1, 2, so this 0.37 is the p-value of the test, the correlation test between the the identifier and the reading variable. Mm, so, okay, no, this for sure it is not because it is not symmetric. So, okay, yes, you see, look, the probability values are the p-values. So let's look only at the lower triangular part. This gives us the p-values of the correlation test. For instance, we computed the p-value between the identifier and the reading score, and it produced us like a p-value of 0.03. Here it is 0.02. It probably uses another test, but it gives us the p-values. What is on the upper diagonal part? It is the same test, but the p-value is adjusted for multiple testing, for dealing with the problem that I told you, because if you test many stuff, you have to adjust your p-value. So if we were only to test these two identifiers, we would use this p-value, but we have to know it in advance. Cioè, we should first fix two pairs. If we instead we want to test the whole matrix without caring about choosing, we need to adjust our p-values, and the actual p-values are the one in the upper triangular part. So and why they are okay, why they are okay, let me simply look for the okay, I want to simply to look at the at what this command does. So probably let me simply type question mark with core test. Let's see. Okay, so the output. Okay, here it explains the test it uses. Core test uses the core function to find the correlations, and uses the test that uses the core. And so what are this it uses by default the method of Pearson, which is the same as core, and it uses by default an adjustment of the p-values, which is the Holm adjustment, and so let me see the output. What is the output? The value. Um, um, So it gives us back the matrix of correlation, which was the first output. Then the values of the t-test for each correlation. Okay, so those are the values of the t-test. Then the p-values for the adjusted for multiple tests above the diagonal. Okay, so yes, it gives us the I don't understand why though why gives me it gives me that they are not correlated because they are really correlated. So I need to, okay, let me plot core plot. Yes, and let me use now core test, maybe way is better. No, it's the same. Probably I should skip this part. No. Ah, okay. No. Well, now the correlation matrix is the exactly the one given by core. Uh, yes, it is the same matrix. So now it is okay, and then these are the p-values actually. So now on the diagonal, there is nothing to test because it's the variance. Well, here we have the p-values. So, okay, was something wrong with the code? I don't need to do the this core test requires a data frame as an input, and I was passing it a matrix, which was wrong. So now this is the right are the right p-values. So on the lower diagonal part, we see the p-values that are not adjusted. On the on the upper triagonal part of this matrix, we see the p-values that are uh, adjusted. So, for instance, they can change, and actually they change because here we see a 0.01, which is smaller, and here a 0.02. It's still significant, but a little bit higher, and it could make a difference. Here we see that there is not really so much difference. We can also we can choose other methods of adjusting the p-values. Let me say again, this adjustment is due to the fact that we are doing many tests. And okay, maybe let me do it. No, I will do it in the next lecture, and I will go back to this example later. But simply to say that you cannot test anything for free. If you test at least, if you test many stuff, the chance you are doing something of a positive result by randomness also increase. So you have to take into account that. And we can use also other methods like the adjust method, which is called Bonferroni, which is a classical choice. And it should be, okay, now it changes a lot, the p-values. Look, from 0.04 to 0.54, it's a lot. From 0.01 to 0.12, it's a lot. But other were really so small that also the Bonferroni correction doesn't change them. But for instance, the math ID score passes from 0.00 another decimals to 0.03. So if you are doing this on block, you should look at the upper triangular part. So mm, this is like, I don't know. I will go back to this p adjustment method later. Now let me do I don't want to do another test to explain which statistic behaves is used to compute this test. So let me do, what can we do if we don't know, uh, if we want to create a test? So we want to test the fact that H0, this hypothesis, that H0, that this correlation is equal to 0, or we want to test this other uh, hypothesis. Now, what can we do? Well, we need to say we can take we take a sample. So, for instance, let's try. We look at I don't know, the correlation between the math score and the reading score of the same student, yes, and we obtain a value. No, we do not obtain a value. Why? Because there is not core function, but it is one with only one error, and we obtain this value. How can we say we say that whether this value is big enough, big enough? Well, we need to know how rho distributes if H0 is true. How can we do it? I mean, well, actually, it is actually possible in this case. It's like a smart way. Actually, I find it very smart because we can simply, like, we are seeing students. Well, okay, maybe let's not do it for the students. Let's come back to the example of the heights and the weights. So it was the beginning of the lecture. So we had the Moscow population, which had some heights and some weights. We record their heights and their weights, and we have this table, which we save in data. So and we take samples. So we can take a sample, and okay, we save this sample in the sample variable. We observe the correlation between the sample weight and the sample height. And we obtain a value, which we will see later because now it's occupied my computer. What do we do to obtain uncorrelated variables? Well, we can sample, we can mix the variables that we have sampled. So we take this so we want to put them as if they were uncorrelated. So we go back. Well, a way to sample the same data but uncorrelated is to mix the two vectors, the heights and the weights. So if I plot sample weight and sample height, okay, heights probably and weights. Okay, we see that the data is dependent. But we can do this following stuff. We take the vector of weights and we order it again. So we take heights mixed, which is simply the vector of heights, but we mix it. So we use this command which orders the vector. So we can do this command and okay, so mm, okay, we simply sample from the vector sample heights with replacement. How much with size equal to the length of sample heights. Okay, this code, what does do? What does this code do? Okay, equal false. Size okay, why it is not used? Okay, why sample is not working here? It requires a vector, which is sample heights, then the length of probably what's called ensample, and then replacement. Okay, sorry. and sample is 100. The length of sample heights should be 100. Yes. Then if I pass to the sample side, the sample heights, the size 100, and with the replacement, without replacement, give me a vector. Why this? It tells me that, okay, this is unused. Okay, replacement. Ah, replace. Okay, it was simply a syntaxis error. Not a okay. Now, what does this do? It simply orders the vector. I am ordering, not, sorry, I'm mixing, disordering the vector. Now, I can compute the correlation between the vector of weights, sample weights, and this new heights mix. But now they are independent because they are not anymore the same person. I'm like taking the weights from one person and the heights from another one. So the row, now the hypothesis zero is true for this row. I can do it many times and the result will change. So I can plot the distribution of this row if H0 is true. So I can repeat this many, many times. So let me do it actually. So I can do this one, we'll put it here. So I do this for I in 1 to 1000. I do this stuff here, and I save the result into many core in this vector. We have to many core is equal to the vector, a vector of mode of 1000 components that the mode is numeric. Okay, this is not a way in which you code in R because you don't use 4 cycles, but I can plot the histogram. Is the histogram of this vector many core. And this is how rho distributes if H0 is true, because I'm so I am mixing, I'm taking the weight of a person and the height of another one. Another one randomly chosen. Therefore, H0 is true, since the variables are independent. I can approximate the density, the not the density, the distribution of rho provided H0 holds. So it is more or less this one. Can do it for more elements. So, okay. It is more or less this one. And now I can compute, well, I can see whether I can take this vector of many core. So many core is we take many core as the distribution of H0 provided of rho provided H0 holds. We can take the quantile function. So we can take the quantile of many rows. So we can take hist many core, sorry. Take a vertical line ab v line at x equal to this point here, which is our critical point. Is where, let me first plot and then explain what it is. Ab line uh, okay, vertical, okay, it is V. Okay, so um, so on the right part of this red vertical line, like 25% of the data fall on the left. So on the right, you have only 5% of the data. So let me also add the line of where our real correlation is found. Our real row is found. It's found in sample. So let me do this code. So like our row that we found is like the black line. The red line is the like our critical row. 95% of the data fall on the left, 5% of the data on the right, included our results. So our empirical test tells us that so the p-value, the critical point row is computed using the above approximate distribution. So um, I will explain it better next time, probably, because now it's late. So sorry for that. But what I wanted to tell you is that you can do stuff also when you don't know the distribution under H0. If you have a way to approximate it, you can do a test. So this is a case in which we could like look at the distribution of rho if H0 is true. We need some assumptions. But here we can really simply force, we can sample from this distribution also. And if we can sample from this distribution, we also know if the sample size is really, here we are sampling very, very big, we know the distribution. So here we are sampling many times rho if H0 is true, and we are approximating the distribution. Then we think that this is the real distribution, and you do the usual test. So we take alpha equal to 0.05, and we look at the point where on the right you have 5% of the points, and that is the critical point. And this is what your quantile function does. So I'm sorry if this was done in a rush at the last moment, but I will come back to it. So I don't know. I will send you some exercises concerning the t-test tomorrow, and correct the exercises that you sent me. Sorry for being late. Okay, have a nice weekend, you all, and see you next week. If you have any questions, write me an email, so I will answer.